This is lecture number 25 of the course ME314 Fluid Mechanics 2, and this is the first lecture of this week. We have already started the topic of turbo machines, where we have done related with the pumps and their performances. Today we will talk about turbines and its different types, and the lecture content would be first the definition of turbine, and then the classification of turbines, and we will go into different schematics of a special class of turbines, what we call it in hydraulic turbines. We will look into the velocity triangles associated with different types of turbines. We will one of the classification is based on the energy conversion process. So we have classification as impulse turbine as well as reaction turbine, and then in the end we will go into the concept of the degree of reactions, and then we will look in the end the application ranges of different types of turbines. So hydraulic turbines, as you know, the turbine is a device that extracts energy from a moving stream. So you have shaft work which is available, which you extract from the energy that is present in the moving stream. So obviously turbines are actually generating energy, in a sense that whatever energy is available in the fluid stream is transformed into the shaft work. So there are two types of devices we already know. One is energy consuming, we call it pump, and other one is which is extracting energy, that is called as turbines. So if your working fluid of the turbine is water, then such a special class of turbines are called as hydraulic turbines. As you know, the turbines, if the working fluid is steam, then it is called as steam turbines. If your working fluid is gas, then it is called as gas turbines. There are different types of classifications based on energy, based on the working fluid, based on the direction of the flow of water. So we broadly classify water turbines in which the working fluid is water. They are called hydraulic turbines into two broad categories. One is called impulse, other is called reaction. And I mean, their idealization we will look into the detail later, but impulse turbine, the example is a Pelton wheel, and which is the direction of the flow is tangential. Whereas in reaction turbine, the example is a Kaplan turbine, which is actually an axial flow turbine. It means the direction of the flow of water and the axis of rotation are parallel. So, and then it is actually called as an axial flow. So if it is mixed flow, so partially it is in the axial direction, partially it is in the tangential direction, then we call it a reaction turbine. So Francis is part of a reaction turbine. If you look at this, is a picture of a Pelton wheel. So there is a jet of water which is striking to the blade, and blade rotates, so your shaft is in rotation. In an axial flow, the direction of the flow is parallel to the axis of rotation, and then you can see this is a shaft which is having a blade, what you call it a propeller. And this is an example of a Francis turbine, which is actually partially axial and partially tangential, or what you call it, even if it is in the radial, some flow is in the axis of this blade runner direction, that would be in the radial direction. So the idea behind exactly the same as in the pumps, you have axial flow, you have radial flow, and you have some pre-wheel component. So this is exactly the same. This is a typical arrangement of a reaction turbine, usually the Francis turbine, which is much common. So what you can think of, this is the blade. So and this section is actually the gate where this is a gate which is opened, and usually that is actually called as penstock. This pipe where fluid is coming. So what we do is, in hydraulic turbines, obviously because working fluid is water, so you store water in the dam, and this is the level of the water in the dam, and what you call it, an upstream pool, and this embankment is and the shape, as you know, that pressure changes with the height. So more the height of the water, more with the pressure exerted. So that's why this is an embankment support in order to bear that weight. So fluid comes from this penstock and having that energy stored, and then you have a guide vanes. Actually, this is actually your shaft portion, and this would be your blades, and before the blade you have some guide vanes. So first fluid enters into the guide vane and then goes into the runner, and then obviously whatever fluid imparts energy to the shaft, and shaft is in rotation, and that power is transferred to the generator, and so that we can generate power, and whatever fluid comes in through this tailgate, that actually it is usually a draft tube, not shown here as a draft, but usually it is a draft tube, and this draft tube takes the water out, and then it goes into the downstream side of the dam. If you see its cross-sectional view, because this is a front cross-sectional view, but if you see this this A is a cross-sectional view of the plan view. So if you see it from the top, what you see here is the fluid is coming from that intake. The fluid is coming in, and then first it enter into the adjustable guide vanes, what you call it, a wicket gates, and then it goes into the runner of the blade. So what you call it, a turbine runner or Francis wheel, and then fluid enters from the outer periphery and leaves from the inner periphery. So this is something opposite to the pump. So eventually you got this. So this is actually the cross. If you see it from this cross section from the top, it looks like this. So this would be your runner blades, this would be your guide vanes. So this same Francis turbine, okay, this is actually so-called draft tube. So this section is actually a diffuser passage, and this level of water, which is it is actually called as an head race. This level of water, and this level of water is called as tail race. So head race to tail race is, head race is the highest level, and the lowest level on the downstream is this where the fluid is going out, is actually called as downstream, and this is that is actually called as tail race. So this is actually the tail race. So you see, this is your guide vanes. This is your guide vanes. This is the section, volute section, through which the fluid is coming from the penstock, and once it goes into this guide vane, and then this guide vanes guide the fluid to go into the runner, where it imparts energy to the shaft, and the shaft starts rotating, and the mechanical power is generated, and then mechanical power is converted into electrical power through generator. So the typical this is actually the cross-sectional view of this Francis turbine from this power plant in Brazil. So if you see it from the cross section, just this view, so these are your volute sections. This would be your volute sections, and this would be your mixed flow type runner, so which is actually the closed runner. And then obviously you have arrangement for generator and power transmissions, and obviously you have gearboxes and all that thing. And this would be your draft tube at the cross section, where the fluid is going to the downstream side. This is a big precaution, a big view of that blades impeller of this Francis turbine, which is actually the fluid enters from the volute section and then leaves through first through the guide vane and then through the impeller. So this is actually the picture of an impeller, which is actually the runner portion of the turbine. And for understanding, I mean, there are 17 blades here in this, and their outer dia is 20 feet. So 20 feet is that dia, and the RPM for that is 100 RPM, and it produces a power of 194 megawatt, and the volume flow rate is in the order of 375 meter cube per second, and the net head available would be for that turbine is 55, around 55 meters. So this 55 meter height, the water should be stored so that you can run that turbine and you can generate this amount of power. If you see more closely their velocity triangles, and you see this is the plan view of their runner, where this is a guide vane, fluid enters through a guide vane, and then one is the cross section at the runner, and this is the 2 is the cross section where it is leaving from the blade. So if we have this angular speed of the runner is omega, and the velocity triangle at the guide vane angle would be this is your tangential velocity component u1, and alpha vane is the angle which your absolute velocity of the fluid makes with the tangent. Since fluid tries to enter by this way, but since the blade is moving in that direction, so that would be the relative velocity, and the angle which makes with the relative velocity in the tangent would be beta 1. So I will use the same notation and the same nomenclature which we have used for centrifugal pumps. In case of centrifugal pumps, fluid enters from the inner periphery and leaving from the outer periphery. In turbines here, fluid enters from the outer periphery and leaving from the inner periphery. So this would be your tangential component of the velocity, which is we have seen that initially that is energy that is available is that is to be converted into shaft power would be from our Euler equations of turbo machines. You know, it is depending upon the product of the blade speed and the tangential component of the velocity, which is v theta 1, which is much bigger at the inlet and much smaller at the outlet, so that the energy available is having this and is transferred into that. So the same composition for the available head converted into kinetic and potential heads, the same has to be applied in turbines as well. So I'm not mentioning as we have already seen in pumps. The difference between pump and turbine is just the opposite action. In pumps you are actually your shaft power is transferred to the fluid power, and in turbines your fluid is extracting power from the moving stream and from fluid power to the shaft power. So actually they are just opposite from energy transfer point of view. The rest is actually the same different types of velocity triangles are present. So typically you have a bigger velocity triangle at inlet and smaller velocity triangle at an outlet, at the runner outlet. So energy is imparted, but we will see how this energy transfer takes place, what energy transfer takes place in the guide vane and what energy transfer takes place in the runner. We will look at when we'll talk about degree of reaction, but right now it is exactly the same notation, and we have already done the same thing. Your absolute velocity of the fluid is decomposed into two vectors. One is the tangential vector, which is v theta 1, and one is in the radial direction, we call it vr1. Radial direction is nothing perpendicular to the tangential direction. The same is true with this velocity component v2 is transformed into two component vr2 and v theta 2. So this V2 is the absolute velocity of the fluid, which is transformed into two components. So one is in the tangential direction and other one is in the radial direction. So same equation of turbo machines to be used to calculate the power which has been transferred from the fluid to the shaft, and same type of working is required. If you see another type of turbine, which is actually an axial flow turbine. So in axial flow turbine, you see the fluid enters in such a manner that this is an axis of rotation and the direction of the flow is parallel to the axis of rotation. And so you have this propeller type blades where you have a shaft and a hub, and on that hub you are mounted blades. So they are actually called as runners. And the same is, they have also the guide vanes before entering into the runner. There is a fluid transfer takes place in the blade passage, what you call it, through the stationary vanes, and this is the runner, which is actually the rotating vanes. So these are the stationary vanes, and they usually have this their angle can be changed at different positions, so that that would determine the angle by which the fluid enters into the runner. So this is the cross-sectional view, front view, and this is the plan view of the same thing. And obviously it has this cross-sectional view for this axial flow turbine looks like this, in which you have arrangements of some mechanical components like you have generators, and you have gearboxes, all are installed in one assembly. So this is an example. Axial flow cup line is the name of class of turbine, which is actually an axial flow turbine. And now see the velocity triangle for the axial flow turbines. So you have the shaft which is running, and this is a casing and having guide vanes, and then you have a runner, and through that draft tube the water goes to the downstream side, and the level of water would be called as tail race. So your velocity triangle a little bit different in case of this. So this would be the aerofoil section of the runner blade. So the tangential speed is u, which is omega times r. So this would be your tangential velocity, and fluid tries to enter with that velocity, and due to that blade velocity, that would be its relative velocity. And the same nomenclature we have used. The absolute velocity is divided into two components, tangential component and the radial component. And there is a typical velocity triangle at the outlet of the runner. So your V2 is having only the radial component. It means the tangential component here is 0. So the fluid goes in the radial direction, and this would be the direction of the blade, which is actually the same at the inlet of the runner, and the same is at the outlet of the runner. And W2 would be its relative velocity at that outlet. So very slightly the nomenclature is the same, the equations are same that we have used for pump, the same to be used for turbine. So we don't need to do it again. Exactly the same working is applicable. There is a third type of turbine, which is actually called a tangential flow turbine. So in tangential flow, there is a fluid jet which comes from the nozzle, and that strikes to the blade passage, and these buckets of the blades are struck by that, and so the momentum of the water is transferred to the blade. So once this momentum is transferred, so this energy is imparted to this wheel, what you call it, a turbine runner. And this is the front view, and this is actually the side view. If you see, this would be your shaft of the turbine which goes to the generator, and this would be the buckets flow in this bucket at that cross section. So there is a symmetrical flow. I mean, some fluid goes in this way, and some part goes to this part of the blade, and some part goes to this part of the blade. And the blade buckets are like that. You have some symmetrical shape of the bucket, and so fluid enters, the jet enters, and then fluid moves through the passage of the blades by transferring momentum, and we will see the detail shortly. Right now we just see the schematics and their corresponding velocity triangles. So here, since at the inlet the velocity triangles is a straight line, because your v1 would be the jet velocity, so which is actually the combination of the relative velocity and the blade velocity, because this blade is moving with certain speed. So then when this would be your control volume, and it is symmetrical in shape, the blades are symmetrical in shape, and so the fluid leaves the blade by transferring momentum to this blade. The same force, and that force is responsible for turning that wheel, and the velocity by which the jet is leaving the impeller blades, W2 is its relative velocity, V2 is its absolute velocity. So you have some bigger velocities at the inlet, and energy is transferred. So at the outlet you have some smaller component of the velocity, so energy is transferred from the fluid to the blade through rather to the shaft through blades. So these are the typical velocity triangles for we have seen for 3 different types of turbines. Okay, now we formally define different types of turbines. So what you call it an impulse turbine. Actually, the definition of impulse turbine is just based on their energy conversion process. So in hydraulic turbines, available energy is in the form of the total head. Total head means whatever the potential head, whatever the kinetic head, whatever the elevation head you have. So that would be your total head, and whatever the energy you have available in the water stream, that has to be converted into kinetic energy through the nozzles, and that velocity jet strikes the blade, and the blade is attached to the periphery, and so the pressure drop in the blade is no pressure drop takes place in the blade, so pressure is constant through the blade passage. So what actually happens is the jet velocity jet which transfers momentum to the blade. So there is a change of angular momentum, and rate of change of angular momentum is actually as torque, and torque multiplied by the speed would be called as power. So that is actually, so whatever the energy available in the form of the head is directly converted into kinetic energy, and then this momentum interaction, what you call it, once force is applied for a short interval, that would be called as an impulse. So that's why it is actually called as impulse turbine. So the one of the biggest feature of this turbine is within the blade passage, actually the expansion is not taking place. So it means the pressure drop is zero within the blade passage, or through wheels there is no energy transfer is taking place. Because of that, or whatever the energy transfer takes place is whatever energy available is directly first converted into kinetic head, and then this kinetic energy is transferred to the blade, so the pressure drop within the blade doesn't take place. Look at this velocity triangles for such impulse turbines. We can think of, let's say, if there is certain angle through which the fluid tries to enter, and this is the direction of the blade speed, so that would be its relative velocity. And if this this angle by which makes if it is some angle with the tangent, that would be your alpha 1 actually. So this velocity vector is divided into two components, a tangential component and a radial component. Radial component is not shown here, only the tangential component at the inlet is shown, which is a much bigger value. And if you see correspondingly their relative velocity, so what happens to their I mean, it could be this one or it could be either this one, but in each case what you see is absolute velocity at the outlet is much smaller than the absolute velocity at the inlet. So absolute velocity at inlet is actually your jet velocity. So whatever your available energy is converted into kinetic head, and this jet velocity is representing actually more that velocity, more will be the available energy to the fluid, and this same energy is transferred to the shaft, and once the fluid leaves an impeller, its velocity v2, which is smaller than that. So your impulse turbines absolute velocity at the outlet is always smaller than the absolute velocity of the fluid at the inlet. There is not much appreciable change takes place as far as relative velocity is concerned. So W1 is nearly the same as W2, because if you are assuming that there is no friction takes place in the blade passage, usually there is a slight reduction, but it is not due to the theory but due to the effect of the friction. So relative velocity in impulse turbine are constant, whereas absolute velocity of the fluid decreases from inlet to outlet. And another feature for that impulse turbine is that the blade patches are once it is a jet, then obviously the jet strikes and some part of the fluid is just focusing on the blade passage, not the whole part of the blade patches is filled with the water. So your blade passages are not completely filled in case of impulse turbine, and they are actually the tangential flow turbine. And these another feature is the blades are symmetrical. So whatever the jet is, bifurcates the flow into two parts. So the blades are designed such that they are symmetrical. Okay, now see the reaction turbine. So in impulse turbine, what is happening? All the available energy is converted into the jet velocity, kinetic energy, or the jet velocity, and then this momentum interaction takes place and energy transfer takes place from the fluid to the shaft. In reaction turbine, what we do is we do the energy transfer process in two parts. So only in the first part what happens is whatever the total head is available is converted into kinetic energy by a ring of stationary guide vanes. So all that energy is not converted into kinetic energy. In guide vanes only they are stationary part, so only the that's why we call it an stationary guide vanes. So the guide vanes are such that the whatever the available energy is first converted into some kinetic energy. So these guide vanes actually act as a nozzle. Your passages are designed such that they act as a nozzle, so that the some of the energy is converted into kinetic energy, but still they have some pressure energy available. So what happens is, and then this fluid enters into the runner, where the remaining energy, that is actually your pressure energy as well as your kinetic energy, because you have both forms of energy. So in the runner, this pressure energy is converted into kinetic energy. So in reaction turbines, this energy interaction takes place in two parts. First, it into kinetic energy that takes place in the stationary guide vanes, and the remaining, so it means in the runner blade passages there is a pressure drop takes place, whereas in impulse turbine we have seen that there is ideally there should be no pressure drop. So the one of the main difference between reaction and impulse turbine is that in reaction turbine there is always a pressure difference through the runner. So it means delta P is not zero and expansion takes place in the runner. So some part of that energy is converted into the runner. And what we see is, if you look at closely the velocity triangles in the reaction turbines, so the relative velocity usually increases through the runner. So we have seen that in impulse turbine the reaction relative velocities are nearly the same, but here once the fluid enters the relative velocity increases. So if you see here the jet through the guide wings coming to this reaction turbine, so this is the absolute velocity of the fluid, this would be your blade velocity, and this would be your relative velocity. So what is happening actually, once the fluid passes through the runner blade, so that is actually the inlet at the runner, this is the outlet at the runner. So here W2 is much bigger than the W1. So there is an increase in the relative velocity. If you look closely, their velocity triangles. So since I have not drawn these triangles to the scales, but once you will put according to the scales, then it would be more evident. The same is true with this reaction turbine, in which you have fluid leaving only in the radial direction. Here also you see initially your relative velocity is W1 and your relative velocity at the exit of the runner is much bigger. So the in reaction turbine relative velocity increases through the runner, whereas in impulse turbine the relative velocity is nearly the about the same in their runner. Unlike impulse turbine, where blade passages are not completely filled, here the blade passages of the runner are such that they are completely filled by the fluid. Okay, so now we are in a position to see the concept of degree of reaction. So let's say the available energy is in the form of the head, and I call it an head. H would be the available energy, and we apply energy equation to the inlet and outlet of the runner. So your if you are ignoring the altitude heads, so you have a pressure head, you have a kinetic head, that is actually their head actually available at the inlet of the runner, and obviously whatever energy is available is converted into pressure head and kinetic head, and the H, that is actually the energy that has been transferred to the turbine, so the turbine head. And we will see this energy equation in the next lecture more closely. Then you will see you have sum of all the heads plus head of the pump, and you have sum of head plus the head of the turbine plus the head losses. So here we are ignoring the head losses, we are ignoring the altitudes are considered at runner is exactly the same, because runner inlet and outlet are at the same altitude, and so this would become our energy equation. So what I do is I just bring this energy equation in such a manner that H is on the left hand side and everything on the right hand side. So this is something that actually the energy transfer per unit weight of the fluid that has been transferred to the turbine. So actually that is actually your turbine head. So that depends upon the difference of pressure and the difference of drop in the velocity head. So as we see in reaction, the velocity at the absolute velocity at the inlet is much bigger than the absolute velocity at the outlet. So that is actually the part of the energy that is available is converted into pressure drop and in kinetic head. So this pressure drop, some of that pressure drop takes place in this blade passage. So if you look at your class of impulse turbine, where pressure drop is 0 in the runner, so that term would be 0 in case of that impulse turbine, then all the energy available is converted into kinetic head, that is increasing the jet velocity. So because the pressure drop is 0 in case of impulse turbine, but in general this would be our equation. The concept of degree of reaction is nothing that is the total energy available and the energy available due to that pressure drop. So if you take the ratio, that would be called as degree of reaction. So if static pressure drop is 0, then the degree of reaction would be 0. So that is actually the R0 would be a special case in your impulse turbines, because your pressure drop would be 0 compared with the total energy available. So I substitute here these static pressure drop in terms of head would be difference of the pressure divided by rho g, and the total energy transfer that takes place would be h. So that would become the formula for calculating the degree of reaction. So if you substitute here, as you know, this term is h minus this kinetic part. H minus this kinetic term would be that pressure drop about total head. So if you simplify this, what you end up with, h and h would be cancels out, 1 would be there, 1 minus this thing. So that would be the formula. If we know velocity v1 and v2 from our velocity triangles, we can easily calculate the degree of reaction associated with your turbine, and h is the head which is actually available for you from the fluid that has to be transferred to the shaft power. So that would be the, actually h would be the head of the turbine here. So as you know, if your ideal case in which v1 is same as v2, then the degree of reaction comes out to be 1 here. Or if in the opposite case, if these two numerators and denominators are exactly same, so it means your degree of reaction would be equal to 1. So we can say if v1 is same as v2, then your degree of reaction is unity. Then it would be called as a pure reaction turbine. So this is of course in idealization, v1 is always greater than v2. So if this is the case in which if happens the velocities are exactly the same, then it would be, your degree of reaction would be unity. Opposite case would be if your pressure drop is 0. So if your P1 is same as P2, then your degree of reaction is 0. So if your degree of reaction 0, it is actually called as pure impulse turbine. If your degree of reaction is 1, it is called as a pure reaction turbine. So actual turbines are neither pure impulse turbines nor pure reaction turbines. So it depends upon how the total available energy is converted into pressure drop and kinetic head. So that proportion gives us an idea about how the energy conversion takes place. So in impulse turbine, since all the pressure drop in the blade passage is 0, so all the available energy is converted into kinetic head. So in that case, your degree of reaction would be 0 here, because pressure drop is 0 here, so your degree of reaction would be 0. In case of pure reaction turbine, velocities would be same, then the degree of reaction would be equal to 1. I mean, there are different types of turbines available, and their parameter of interest for us is the head which is required to run the turbine, and the flow rate of the water, which is in meter cube per second. And we have seen that for 194 megawatt, it was in the order of 375 meter cube per second. That would be the flow rate. So and here the scale is less than this, it would be 0.1 megawatt. Here it is less than 1 megawatt, and it is something less than 10 megawatt. It is something less than 100 megawatt. It is less than something thousands of megawatt. So, and the head is also not a linear scale, starts from 0 to 10 meter height, which is a low head turbines. And then you have 0, 10 to 100 meters, so which is a high turbine, and 100 to 1000 is much higher turbines. So if you see, your Pelton wheel is something where your flow rate is very, very low, and your head requirement is much higher, and typically you can get up to less than 0.1 megawatt or something 1 megawatt range. So this dark color is actually called as Pelton wheel. And then you have less dark color, which is actually called as pump turbines. So pump turbines are actually when your turbine is moving in the reverse direction. So pump and turbines are just opposite in their action. So if you see Francis turbine, which is a mixed flow turbine, Kaplan is an axial flow turbine. So much lighter is actually called as an axial flow turbine. So this would be the range in which power and head requirement is in that range. So here you see there is Ghazi Barutha, which is in Pakistan. So that project, that hydro turbine is in Khyber Pakhtunkhwa. So that is actually the Francis turbine. They have a mixed flow turbine, and it is in the order range of something. One each turbine is order of about 290 megawatt each. So they have something 5 turbines on the same dam. So something about 1450 megawatt is being produced overall here. So and obviously you can see this at that place how many meter cube in hundreds of 400 500 meter cube per second is the requirement of the flow, and they work in the order of 96 or 90 meter head is the requirement for such turbines to work. So there are different classifications, and if you see this bulb, pit and S turbines is actually nothing. This is a cross-sectional view of a bulb turbine. So you have a rotor blade and you have an axial flow turbine like that, and there is a bulb-like thing in which all the generator accessories and gearboxes all are integrated in that bulb. So your everything is in that bulb actually. So that's why it is called as bulb turbine. So these would be your blades, and sometimes on that you have make a pit and you put that bulb and that turbine in that pit. So these are the stairs go into that pit. So they are called as pit turbines. So they, I mean, in these turbines, not only the turbine is there, but runner, your gearboxes, your generator, and all the accessories are shown here. This is an example of the cross-sectional view of an S turbine and the generator. And the classification is because these pit and S turbines are working with a small head, like 10 meter, 25 meter head, and they're 10 megawatt range, something like that. So for a small power requirement, when your small head is available, you can install such turbines now. So it all depends on the flow rate requirement and the head requirement. Is both requirements are required for different applications. So this is at this point we have an understanding of different types of turbines and the energy interaction, how it takes place, and the concept of degree of reaction. So we stop today's lecture at this point.